accelerators in Europe. We're now going to switch topic a bit to payloads for CubeSats, and I mentioned earlier the successful hyperscalt demonstration on the GOMEX 4B spacecraft. So our next talk is about that. I'd like to welcome our speaker, Marco Esposito from Cosine Measurement Systems here in the Netherlands. He's business unit manager for remote sensing at Cosine, and he'll talk to you, of course, about this wonderful instrument we have in orbit now. Thank you.
Thank you, Roger. So the audio is good, right? Do you hear me well? Very good. So good afternoon. Thanks for listening to me. I will be presenting, as Roger just introduced me, hyperscalt. It is an hyperspectral imager for nanosatellites. And actually, I'm going to mention two missions. The first one, that is demonstration of GOMEX 4B, that is currently running in orbit. And the second one is in production. It's going to be launched early next year. These are both nanosatellite missions. Few words about Cosine. Cosine Measurement System is a Dutch company, actually a few kilometers away from here. Counts 45 heads about, 30 of which are PhD level in remote sensing, optics, photonics, just to give you an idea of the education level in the company. And we work for space, mainly we come from the science, space science. So actually we have a lot of knowledge about miniaturization, and we are trying to apply all this knowledge now to the Earth observation market. So at Cosine we do hyperspectral is one of the most, let's say, historical technology lines we are working on since 15 years. But we do also thermal infrared. Actually, we have big plants also there for temperature mapping. We do LiDARs. We are carrying on a few projects. We design technology development for LiDARs, and we hope to find, let's say, a way to demonstrate in space also for nanosatellites. So hyperscalt, what it is? This is hyperscalt. This is a 1.3 kilograms payload, so mainly optics and some electronics that you see on top of the stack. So we can say that is the first ever of this size, of this class, fully fledged hyperspectral cameras, 45 bands visible to near infrared, about 14 nanometers spectral bandwidth. As also Roger mentioned before, the asset here is not about spatial resolution, it's about spectral resolution. So you get all this information you're seeing and a large field of view. Let's say if it is fully exploited, we have about more than 300 kilometers worth with this kind of characteristics. So offers, let's say, enabling constellation for very high revisit time, but constellation not of mega, but a few units, you actually start to get very interesting revisit times. The assets of these payloads lies in two sides. One is on the optical part, so it's all free-form optics, so we exploited the latest technologies in optical developments. This has been developed within the ESA, let's say, framework, so we made use of many other projects in coatings, again, manufacturing, metrology. So it's really state-of-art in this regard. And we spent a lot of time and effort to make sure that the telescope, this is a 4 meters telescope, was aligned by manufacturing. This allows to actually produce many more in a short amount of time. So we try to remove all the alignment time that with 4 meters actually can become very long in the lab. And therefore, if you get to constellation, it becomes very useful, you can imagine. The other big asset is that because of when we started, still now, but it's improving a lot, the bandwidth capacity of nanosatellites was extremely limited, even with S-band, so you don't get too far in hyperspectral data. It's actually a bottleneck also for bigger platforms. So we produce terabytes of data per orbit if you want really to have a high duty cycle. So becomes really a limitation. So what we try to do is to build a processing chain in orbit such to get to level 2B, so to the application geophysical parameter in orbit, and download that instead of the full data chain. Of course, we understand we have scientists also in-house, we talk to scientists, so data is still important to see, to download, so we made a very modular software such that you can download any level you want. And so one of the interesting levels is actually what we call level 2, let's say more conventional classification of processing levels, but also nowadays being called ARD, analysis ready data. So actually it's the backbone for any application that we can produce in orbit. And based on that, you can go on with any other application of the customer or any other demonstration. So we can say from now, so people should not be worried anymore about the hyperspectral source, but no, we can start with applications, operationally speaking. Yeah, that's what we try to, of course, try to remove all the processing chain on ground as far as we could. Of course, there are limitations, there are limits that you cannot, let's say, overcome, but for an early warning system, for producing, let's say, a quick look of an event or phenomena that you want to see immediately, and you don't want to wait the time of downloading the data, processing the data, distributing the data, but you just want to get an information with a position. That's what we try to do with us, with our partners as well. The applications we targeted from the start are, let's say, a subset of a large one. So actually we had quite some ideas. We did a first workshop in the start of the project with many stakeholders from ESA, from us, from the consortium, but also scientists that we knew, so from our network. And so these are the ones that we wanted to start with because some are reasonably simple, so you can actually demonstrate the full chain. You can achieve that target. Some are more complicated, like the change detection one. So there are more challenges there to afford. And therefore, we try to have a set that is mixed and try to demonstrate these capabilities. As I said, so one is the application itself, and the other one is the ARD, so the level 2. That's really what we want to make sure is there, is ready, such that any user, any interested party that wants to develop an application doesn't need to bother about the first steps up to the data tube. So we produce a full data tube in orbit, and then the application can follow up on that. Just to let you understand a bit the figures, the performance of the processing speed. So we can get from raw data level 0 to application data, depending on the application, of course, but between 40 and 80 seconds. So in, let's say, less than 2 minutes, you get the information ready. And then depends, of course, on the ground station, depends on the timeliness between ground station and user. But so after that, you can have the information ready on your desk. That's a bit what we try to achieve. And this is an example that we gave to ourselves as a target. So what we want to do, we want to change completely the way the space assets are used. So in one orbit, in this way, we can actually serve multiple applications in real time. So this is one of the revolution, one of the tracks where we have on ground different experiments running from partners. And there we want, let's say, try this kind of experiment. So do one run and try to deliver different information from the same orbit. So talking about Mozambique, Tanzania, Uganda, where we go from flight hazard to floods, change detection, and so on. That is something very challenging. And this provides already, let's say, a good understanding what challenges are behind. And if you scale this with constellation, you can imagine what kind of interesting network you get, what kind of messages you can deliver. And therefore, the size, and therefore also the performance, of course, are not such a big payload, but the kind of service is completely different from another angle. Therefore, it's complementary to the Copernicus, to bigger satellites. That's what we want to achieve. Timeline, so we started with this first user meeting workshop in 2014, mid-14, and then we went through, of course, design, engineering models, qualifications, and finally we launched Hyperscat on the 2nd of February 18 on board the GOMEX 4B platform from China. And from there, so we have now these settings for the operation. So we, at Cosine, we are we call it user home base, where we actually decide finally what to do with the payload, with the experiments. So we are able to send instruction to our payload from Cosine to GOM space that will send information up to the spacecraft, and therefore we can run our experiments. But behind us, there is, of course, ESA. This is one of the most important stakeholders. And then we have the consortium. So we have Vito from Belgium and TU Delft that are providing knowledge on part of the algorithms, and then S&T from Norway that provided some software coding for some of the applications. Indeed, again. And this was a GSTP project, so a General Study Technology Program, and therefore we needed support from delegations. And here you have a list. So from the Netherlands, from the Belgium, and from the Norwegian delegations, we got support, and therefore we were able to develop all this. So after the launch in February, we had, let's say, a first commissioning of the core subsystems somewhere in March. So we demonstrated, let's say, the core, like the sensor, like the readout, the storage, and the downloads of a very tiny image, very compressed and binned, but nevertheless to show that the full chain was working, the optics were in focus, everything was working. We did in March, very quickly, with very low resources in terms of energy and downlink bandwidth, talking about 1 megabyte only. Compared to, yeah, we have about 1 gigabyte per scene, so you can imagine the difference. And after that, we had, let's say, a more complete commissioning that actually was done all in July. So a few months later, the GOMEX satellite is full of experiments, so then we are sharing time, so there is some waiting time that is a bit on the path. After the full commission in July, now we are in the middle of this first operation step. So we are running acquisition over calibration sites. So we depend fully on vicarious calibration. So we are acquiring over deserts, over geometrical sites, spectral sites, and we are in this phase. So we got already quite some acquisitions, not yet completed that phase. So we are a bit behind compared to the schedule we had in mind. Nevertheless, proceeding, and the system is commissioning also together with the platform. So actually now we have a nice chain that works very nice, from Consign to GOM Space Satellite and back to us with data, and that works. What I just said. So these are the two images that we got in March, where we, as I said, we commissioned the core subsystems of hyperscat. What you see on the top was part of the sensor. Therefore, we got, let's say, from 400 to 600 about nanometers spectral coverage. This is Scotland. So there is, let's say, Glasgow on the left and Edinburgh on the right. And so this was a first, let's say, commissioning compressed image that we were able to download and to see that everything was okay, everything was working fine. Then we had, a few days later, another commissioning image of a tuba. And what you see is the image at the bottom. And here actually we get the full frame. Finally, we got, let's say, to see the full sensor, not performance, but qualitatively speaking, let's say the response of the full system. And here you see just what we have been showing already in some other presentation, but qualitatively tell us that the system is properly, nothing is in place, nothing was broken, and so on. So you see also a comparison between acquisition over water and over clouds, and you see on the top right, let's say, standard response of, for example, of water. You see that the spectra are qualitatively the same. So that told us that things were going okay. What happened in the meantime, then from that commissioning to these days, so we acquired other calibration sites. So what you see in Africa, so there are in Morocco, in Algeria, there are, of course, deserts. There are some very well known to the community, used in the calibration community, and they are the same we are using as well. Then we got other images, Japan, North Europe, Poland, and also Cuba, and there is one missing here that is over California. We tried to image during the wildfire period, some of the images from that zone. This is finally what we want to achieve with more data sets, with more also repeatability. We want to see how the system changes compared to different telescope temperature, different conditions. So it's everything leads to a demonstration and characterization of the system. As I said, we are in the first operational slot still, so still looking at calibrations, and it's something that is still ongoing. We made, thanks to, let's say, the acquisition made so far over the desert, some comparison, a bit to start to see whether compared to other systems that are not actually anymore in orbit, but how we compare to. So what you see here, it's Hyperscout, one of our engineering models to the bottom, and on top you see Hyperion, that is one of the I think few hyperspectral systems have been in orbit from NASA, have been working for a decade, but it's already 2 years that has been decommissioned. So actually the data we got was not at the same time, were not acquired at the same time as Hyperscout. Nevertheless, Vicarious site stability was kind of okay, so we could try to do some comparison. Just to show the differences, what you see, the middle column is Hyperscout specification, and the right side is more Hyperion. So just to show the kind of differences that you can already expect. So you see a different pixel on ground, 30 meters compared to 70 meters. But so same order of magnitude. As what the Hyperscout is much bigger. So if you look at the full exploitation is about 350 kilometers, while the Hyperion was much narrower. So if you look at number of pixels, of course technology made progress in this decade, so it's not because of our ability, but it's just technology is improving a lot, so we got much larger sensors that are much easier to be used, to integrate in electronics and so on. So we got a much larger FPA. And in terms of spectral bands, you see that Hyperion goes up to the short wave, to 2500 nanometers. Hyper stops at near infrared 1000. So 45 bands with 14 nanometers spectral resolution. So this one that is in orbit is with these characteristics, but we can also deploy a higher spectral resolution version of Hyperscout by using different technology from IMEC in Belgium, so that we can go to 5 nanometers, more bands. However, you can expect much more data, so again, the problem is there, and there are pro and cons, both concepts, so we will go through them both. The interesting part then is mass, of course. You're talking 1 kilo against 50 kilos, and power 10 watts against 80 watts. These are the difference. What we also compared is the SWOT, so let's say the dark brown is Hyperscout. So as I said, in this case with the GOMSPACE, we had a limitation in the mechanics, so we had to limit our field of view. Still, we get 220 kilometers by 150, so pretty large, while the Hyperion one is more, let's say, line scan. So there are a few pixels along track and a large across track line. So that also shows a bit more flexibility. Of course, you get a 2D data cube, is much easier to deal with. These are the two images, one from Hyperscout, the one on the left, as I said, full frame. You see the spectral variability on one axis, the y-axis along track, and of course on the cross track you get a spatial resolution there. So what we saw from this, we drove different comparison on the spectral response. We see that we see the same features. We also see some differences, and of course at this stage we don't know whether it is the time. Of course these are a few years before, so also these sites are evolving, different seasons, different times. So, but all the features are there, so we see the same features. The intensity we didn't compare yet because we are still going through the calibration, the radiometric calibration, so we have to wait a little bit more before having a full set of figures for the Hyperscout, and therefore we can then go a bit more in details. What we are also trying to do, we got a contract also from ESA to compare Hyperscout data with Sentinel-2 data, and in general, let's say, we are developing a tool to cross-calibrate nanosatellite data with bigger systems. It can be also Landsat 8, can be also other systems. But what we're trying to do is to exploit machine learning to do this. And what we want to do is to make, in this case, Hyperscout having the same instrument response function, or let's say targeted to Sentinel-2, so that users can use the data easily, having, let's say, a common response from the sensors. This what means you get a better spatial resolution from Sentinel, because it's, let's say, from 10 to 30 meters, and you get a better spectral resolution, number of bands from Hyperscout. And so if you get these two together, you get high resolution, high spectral resolution, high revisit time, you get the best of the two worlds. And also accuracy in terms of radiometric is much better because Sentinel has It's a bigger satellite, it's institutional, has calibration equipment on board. So you can imagine why we're doing this, and this is supporting fully that. We also do this with the means of airborne campaigns. So this is going to happen next month, where we want to have, let's say, ground space segment, airborne segment, and a ground truth, so that we can scale up as we want, basically, to cross-calibrate the system and do comparisons. What happens next, or actually not next, but now, what's happening? We are improving the system, so we are adding thermal channels. On top of the hyperspectral to near infrared, we are developing 4 additional thermal channels in the same volume. So the optical part is quite, we made it such we can add stuff inside, so, and that is the result. So we have a contract to deliver this payload for integration to the satellites end of this year, and this will fly in June 2019 in space. So we will have soon 2 hyperscot, one with thermal bands, both in space and capable of doing many acquisitions, so we can start playing with a mini constellation. And the third one is on the, let's say, pipeline, contractually speaking, with the commercial customers. So we can have very soon a very mini constellation of hyperspectral will be really the first time ever. The mission we are working towards to deliver the second hyperscot is FSSCat, is the winner of the S3 challenge of ESA, and is again 2 6U CubeSats that have different payloads on board, and is meant to support the Copernicus land and marine environment services, so Sentinel-1, 2, and 3. This becomes very interesting also because we can share later this data with some users from the Copernicus network, and therefore making progress also on this cross-validation of the data. Applications, so the payloads are not only, of course, not only the hyperspectral, but they have also dual microwave payloads, so on microwave radiometer and GNSS reflectometer. Main use of this is soil moistures and ice extent and thickness. And hyperscot will be used to improve the resolution, so pixel decomposition, therefore getting from not sure now what is the resolution only with the radiometer, but to get to our, let's say, 50 to 70 meters resolution. And that will improve a lot data product. And the bus provider in this case is Tyvek International, so with UPC, that is University of Catalonia, in the lead from the science point of view. This is what I said in short. So we're going to match the data, we're going to fuse the data. They are going to fuse the data, we're going to provide the hyperspectral data, and therefore you will get a solid moisture map at high resolution. And this eventually will be, again, a constellation, so now it's 2, but the plan is to have many more in space. On our side, we have, of course, a big roadmap, so we want to go on. We already got a contract to investigate the adding a UV channel there, and therefore enabling also air quality applications. The final goal is to build what we called here a panorama. So if you can imagine, this is a size of, let's say, a shoebox, again, about 7 kilograms, and you have 4 hyperscot, each of those with 2 bands. So you get from UV, visible near infrared, shortwave, and thermal, everything in this cage, so 7 kilograms and about 20 to 30 watts. So it fits in a 12 view, and you get a Copernicus-like optical subset of data, again, if you deploy a constellation with high revisit, so the application can boost up enormously. There is a website. From this, actually, we're getting a lot of application requests, and therefore we initiate a lot of pilots. Therefore, if you want, talk to me. Otherwise, if you don't manage, just go on the website, send an email, and we can quickly get into business together. That's it.
Thanks very much, Marco. So the time for a couple of questions. Doesn't look like it. So thanks very much. Very impressive capability.